go and attack, you can end up kicking one of these guys off eventually, and yeah. So that's how you could end up with, I guess that's how you could end up labeling one of these if you wanted to, by putting a bunch of water that's labeled. And that sounds expensive, but I guess that's how you would do it. Yeah, you put a bunch of labeled water in with a carboxylic acid. So the equilibrium is just gonna, like, there's no difference, so they're just gonna kind of randomly go. And then if you've got a ton more of this, then most of this in the end is gonna be labeled to some point. So, yeah. Does that make sense? Does that answer? Okay. Did I confuse anyone else more? Cool, just making sure. All right, so nucleophile, water, it is enough of a nucleophile that it can do something. The real test is, do we have a leaving group that's going to make this attack worth something, right? So we do that, we've got R, C, that's L. Did we say in basic solution? No, I think we just, oh yeah, we don't need, right, hydrolysis of acid chlorides. So we're about to do something funny here. I just did something wild. I've got a negative charge on oxygen and a positive charge on an oxygen. Usually, we have to pick one or the other, right? We can't just do both because, I don't know, there's no rules. But that's usually because everything we've done before has required a catalyst. We've required acid or base catalyst to actually get stuff moving. In this case, acid chloride, it is unstable, it is reactive. It's like, no, I would love to get out of here. The chloride is like, I would love to get out of here. So like, if there's any way to do that, awesome, do that, I will leave. So we don't have an acid or base catalyst, which means our environment here is neutral. In a neutral environment, I mean, which one are you gonna favor? Neither, really? So you can have both? So yes, weird, but no catalyst required, hence the weirdness here. Also, when we attack this, we've got a good leaving group, but like, what's a better leaving group than a good leaving group? Pi electrons, because they're not actually leaving, right? They're just sort of blooping up there. So whenever we do this, even if we eventually get rid of this, there's always gonna be this step first. The first thing you break is the double bond to the oxygen, and then you can reform that. Pretty sure that's just the only. Okay, fine, we can do that first. Okay, that's fair, because if we form this first, then that's a better leaving group than this, probably. So let's go ahead and take this color. Water. And we're going to deprotonate this guy so it's not trying so hard to get out of there. Now we've got this, and then when we kick these electrons down, yeah, we could kick the, well, we can't kick this off, right? We could have kicked it off back here, but if we just reformed that and kicked that off, there would be no reason to draw anything because, well, we already showed that happened by putting this back and forth arrow, right? So I'm not saying that doesn't happen, I'm just saying I already showed that part, and so, yeah, that happens, but all right. But once we get here, if this is gonna get kicked down here, this is the leaving group because we already deprotonated this. So now, that guy's the leaving group, and we have too many markers for my hands. Yeah. Okay, fine. Plus Cl minus. Yes? So, this is the way that water kills acid chlorides. Let's see. Acid anhydrides, they also don't need, well, okay, yeah. So either way, low molecular weight or high molecular weight, they are going to react with water, and they're not going to require they're not going to require an acid or base catalyst. If you've got a high molecular weight, then it doesn't react as readily, right, as aggressively. Does that mean that we've got a different equilibrium position, or does that mean we've just got different kinetics? Kinetics, right? It doesn't go as quickly. It'll still react. It doesn't take that vodka hand sanitizer. But my hands were getting very, very dyed. So higher molecular weight doesn't necessarily have a different equilibrium position. It's just that if they react less readily, we're only talking about kinetics right here. These guys, super fast kinetics. These guys, not so fast kinetics. But this also occurs without acid or base catalyst, as with hydrolysis of acid chlorides. Oh. Okay. Guess we don't have that as a mechanism. I mean, the mechanism would be, what is it? That's till 40. Okay. We could do this mechanism. Yeah, we could do this mechanism with the nucleophilic attack and leaving group leaving steps that we know right now. And if you want to do that mechanism, come to my office hours or something. Let's see. Yeah, so let's switch up to ester hydrolysis. Esters are going to need an acid or a base to hydrolyze. So, an acid catalyzed ester hydrolysis, actually, yeah, that's what I thought. Here's the next slide. So these are going to happen at neutral pH. Like, they will eventually reach equilibrium between some of the ester and some of the acid, right, at neutral pH. It's just really slow, like, real slow. Even if you heat it to reflux, it doesn't go faster. And heating doesn't change where our equilibrium lies, right? Heating usually just increases the ambient energy about so that we can do both sides of the reaction faster and we just get to equilibrium faster, right? So usually it just gets us to equilibrium faster. Even heating esters, it doesn't really speed up hydrolysis of esters. So you can heat it to reflux with acid or base, and then you're going to get it happening in an actually useful amount of time. I'm more interested in the next one, but all right. So this one, microscopic reversibility is basically when we're drawing a mechanism and every single step is reversible, so like each of those little steps is reversible, then for the reversible reaction, so if we just draw the like overall reaction between ester and carboxylic acid, we're like, hey, that's a reversible reaction, then we know that from this microscopic reversibility, this idea here, that the forward reaction should be the same as the reverse reaction in like stepwise. The mechanism forward should be the same as the mechanism reverse. And so hydrolysis of an ester in acid is exactly the same as Fischer esterification, just backwards, right? You have this in your slides. We've done Fischer esterification. Give me a no, we can go ahead and do base catalyzed ester hydrolysis, or a yes, go ahead and show us acid catalyzed hydrolysis, please. Can I get, let's do the nodding or the shaking of heads. Okay, cool. We can totally do that. So, Fischer esterification, but opposite. Let's see. R prime. Is it easier or more useful for you guys if we do mechanisms that have R's and R primes, or mechanisms that have, like, versus mechanisms that have, like, actual things here?
I like the R and R prime.
Okay, the R and R prime gives you more of an idea of stuff can be there and it doesn't have to be this. Okay, cool. Then let's keep doing that. Just making sure. Okay. That, just give a black marker. One of these is a less good black marker. All right. That's going to be our electrophile, and we're doing this in acid. So that's our nucleophile, even though right now it looks like this. It still has a lone pair, so it's still our nucleophile, even though it's got a positive charge. All right, so we're gonna attack, right? First step, attack. Oh, I draw these with a carbon now, don't I? Oh yes, this is the much better marker. All right. So now we've got that carbon. Wait, did I say acid catalyzed? What am I about to do? What did I do wrong? What am I about to form? Negative charge, right? Oops. Luckily, we learned that when we're doing acid catalyzed, we're not just supposed to memorize that we protonate things first. We just always find nucleophile, electrophile, do the attack, and then afterwards we check, like a guess and check. So, oops, let's go back a step and do that. Oh, this is a much better marker. No, so right there. And we're gonna have so that, and we'll do a nice quick protonation. Myself. Okay, now we've got that protonated. Now, let's bring in And let's do our nucleophilic attack. And are we going to get rid of this right away? Well, no, because what's way easier to break is just moving around electrons and not actually kicking something off, right? Let's move that around. And we get, ooh, I'm snaking on the board. Are we okay with this today, or? Okay, cool, good. You're allowed to tell me no when I ask that. Like, the only reason I do these things on the board is so that you guys can learn, not like, because I mean, okay, yes, I find it fun because of a weirdo, but like, I do this for you guys to learn, right? So you can definitely tell me, no, do it a different way, like redo it, do it over again in a way that makes sense, because like that's the whole reason I'm doing it, right? Just making sure that we're all on the same page about that. We've got that. We've got that. That should probably be like here, so it's not sideways. We've got OR prime. And we've got a new bond to a new oxygen that has we're going to do that. Yeah. We're going to take the water that we got from deprotonating, or from protonating this. We're going to take the water and attack with the water, because I'm not going to draw an oxygen with 4 bonds. Like, that's just wrong. I'm not going to do that. So, sorry about that. This should be our nucleophile. Not sideways hydrogens. There we go. That. Reversible reaction. All right, now we've got this. This is our tetrahedral intermediate, and we can take some more water, and we can, I assume that's the next step. I should probably check so we don't have to undo things as much, but yeah, that's what I thought. So we can take that, and we can do this, and give us right? Cool. So we're still at our tetrahedral intermediate, but now we don't have to worry about charge there. So now what we're going to do in the end, what we're leading toward, is kicking off this, right? Treating this as a leaving group. Yeah? Because if we treat this as a leaving group, okay, technically we've done some chemistry, right? If we kick off this oxygen instead of this one, technically it's not exactly the same as going backwards, because, I don't know, what if this is a radioactive isotope or something? But like, unless it's actually labeled, and we know that they're different, there's not, you know, there's no point in writing that, right? So this is the one we're trying to kick off to get like a different product in the end, yes? Can we kick that off the way that it is in an acidic environment? No, right? So let's grab H2OH, because I don't want to draw all 3 lines coming out of there. Let's do this, and we're going to go, this guy has lone pairs, and he's going to go, hey, that's a really nice hydrogen. It's a shame. It would be a shame if somebody, you know, stole that from you. Below this, we're not going to be able to see it. So I'm going to leave us here, and I'm going to pull over the other board. This way. This way. This way. Yeah. All right. Are both of these boards in places where you guys can all see them? Okay, cool. This guy is going to go live over here. deprotonates itself, remember, arrows don't show where our hydrogens go. Arrows just show how electrons steal hydrogens, right? Which is the opposite of physics for don't ask me what reason, but when you draw an arrow for current, which current should be just electrons moving, right? When you draw an arrow for current, you don't draw the arrow in the direction that the electrons move. You draw current going that way when the electrons are going that way. It's dumb, but that's physics. This isn't dumb because it's not physics. I'm kidding, physics is fine, but it's only fine. I'm not kidding about their convention for current, though. That's really dumb. Okay, we can finish this before class is over. We've got the same thing, but now we've got this, which is nice because in an acidic environment, in a acidic solution, this guy is now a viable leaving group. So what we're going to do to actually, you know what? When I redraw over here, we're going to do this because can anyone tell the difference between the two alcohols if I don't do that? No. And are either of them labeled? Well, no. So basically, once we get to this point, once we deprotonate it, and they're both... Today's Tuesday. You guys have recitation and not lab? Okay. Real quick. I'm gonna be fast, I swear. They're interchangeable, right? So when we kick this off and form a double bond, it really doesn't matter which one forms the double bond, right? That's why I got rid of that, because if I kept them differentiated, then I would draw this for you twice, because either one could form it. But now, you can't tell the difference, so I don't have to draw it twice, because chemists are inherently lazy. And now we've got that, and we can go, hey, how about this? Just does that real quick. So we have a nice, that is a full arrow. So we can just make our products look like products. And we have an alcohol of the R from this side, right? These are not interchangeable. R prime from that side, that turned into an alcohol, and the R connected straight to the carbonyl stayed there. Yes? Cool. All right. Well, this is exactly the opposite of Fischer esterification. So if you know one, you know the other. And yeah, all right. I will try my best to get your graded exams to you by tomorrow so you can do test corrections. I think what we're going to do is just don't bother writing on the exam because there's just not enough space. Grab a new piece of paper, mark what question you're correcting, and do a mechanism, give a mechanism a whole side of a paper at least. If you're doing like correcting other questions, you can put several on a page. But if you're redoing a mechanism, just start a new page or start a new side of a page. If you have multiple choice to correct, I kind of want, well, no, key, so I guess you could just crack them like normal. I'm thinking if I gave you multiple choice, if I'm giving you what you got wrong, right? Maybe for correcting multiple choice, you can give me like a sentence or two on like, oh wait, no, this isn't right because of this. Actually, this is the answer because of like some sort of, yeah, some sort of short, so I don't want to read a ton, short explanation of like, oh, I was wrong because this is something like that. Yeah, deal? Okay. Yeah, if I definitely get those to you tomorrow, which I'm totally gonna do, then you have until Wednesday to give them back, and you can do, I mean, the ones that you selected for credit on test day, those are the ones that you should redo if you got them wrong. All the other ones, you can do those for practice, but we're not gonna count those as anything. Yeah. And then if you're going to turn it in late, tell me ahead of time, even if it's, or especially, just like in class, right before class or during class or something, so that I don't post that key. Because then you can turn in late work. I am not against late work, I just need to know not to post the key yet. If you missed any recitations, you can email me about that. And basically you can do, the worksheet's already posted. So yes, okay, the key is posted too, but it's recitation, so it's participation and practice. So work on the worksheet, email me pictures of it, and if you missed a recitation, and you can make that up. If you missed a quiz in a recitation, let me know. If that's an excused absence, we can make those up. So, yeah. Actually, I mean, let me know, and we can make it up, honestly. I'm being picky about excused absences, but like really, if you skip them, I have to write a second quiz, so it's slightly more work for me. So like, be considerate and, you know, miss them for reasons that like, well, I kind of have to, and not like, I just don't feel like it today. Deal? Okay, cool. And for exam corrections, I want to say they are open book, note, internet, whatever. But you can't work on them with each other. However, you can work together on similar problems. So if you can find a homework problem or write a problem that's very similar to your homework or to the missed problem on the exam, you can work with the tutoring center on that. You can work with TAs in office hours, me in office hours, each other in group homework, because I think group homework is the best way to learn organic. That's fine. But just make it technically different. Deal? Okay. I feel like that's, you know, I mean, yes, it's honor system, but also we're making a pinky promise. Just not actually, because you don't want this on your hands. Okay. Cool. Yeah. Yes?
Will our exam scores be posted tonight or not?
Yes. Before I give them back to you, they will be. I just have like a couple, like, one that's being taken today, one that I got back from the testing center that I forgot to grade. Yes.
Is there any way to get the verification sheet? I don't know if it's
Yes, well there. It will be posted just like normal, so that's fine. Yeah.
I just wanted to come to make sure that
Yeah,
everyone's-
totally. Yeah, missing recitation is, you can always make up recitation. So like, I mean, if you're just not having it, like,
You said that
question.
posted online? It's gonna be posted.
it'll be posted on, I won't do like a separate announcement when I post it, but it'll get posted in under modules,
Okay.